If you look at this function, this can be written in a form what Slater, which I actually introduced in the last class, Slater determinant, and I had also mentioned that in the 425, but again because of the fact that there is a little bit of heterogeneity, so I am doing it all over again, and this is important for my course. So I write these two functions, this minus this, in the following form: chi1 of 1, chi1 of 2, I will explain chi2 of 1, chi2 of 2, and take a determinant of this. Okay. So if you take a determinant of this, you can see that the diagonal is chi1 1 into chi2 2, and then you take minus chi1 2, chi2 1. Okay. So this function automatically becomes a determinant. If I write it in this form, the trick to write this determinant is the following: that once I know the two spin orbitals, one row should be characterized by one of the spin orbitals. So let us say chi1. The second row should then be characterized by chi2. A column may be characterized by the coordinate of electron. So in this column only coordinate 1 comes, in this column only coordinate 2 comes. Again, when I say coordinate, they are the coordinates of the spin orbitals. So they are basically the space spin coordinates, r and omega, both are there. Okay. So when I interchange, I am interchanging both. So this is the way to write determinant, and this way I can actually generalize very easily for n particle problem. Again, this is not antisymmetrized, this is not normalized, but we can trivially normalize it. Okay. If each of the spin orbitals is normalized, then I can simply multiply this by 1 by square root 2 factorial, and this whole thing will be normalized. So this will then become a normalized wave function, psi of 1 2. Okay. So it's very easy to normalize it. So that's something that we will not worry right now. Assume that the spin orbitals are orthonormal, and we can actually normalize it very easily. So this is the form of a Slater determinant, and in this form lot of things are now obvious. For example, chi1 could never be equal to chi2. Something that I analyzed and found that does not have, it becomes 0, because moment I do this, it is of course two rows are identical, so the determinant would become 0. So that was the reason the wave function would have become 0. Because of the fact that it is determinant, the interchange of any two coordinates will always become negative sign. So its antisymmetry is automatically guaranteed. Okay, and then we find that to guarantee the antisymmetry, the two rows cannot be equal. So two spin orbitals cannot be equal. So that's the statement of Pauli principle. Okay. So the determinant automatically guarantees lot of things. So you don't have to analyze the wave function and keep writing what would generate a antisymmetric combination, right. Here for 2 particles I could do that, but for n particle it will be very, very difficult, because when I go for n particle, I require that the wave function must be antisymmetric with respect to interchange of any pair of coordinates, any pair, any 2 particles. So that will be very, very difficult by a manual analysis to write down the combinations. So what we like to do is to use this idea of the determinant for n particle. So now from 2 particle, I am trying to generalize this to n particle. So for n particle, how many spin orbitals will be required? N. Now from the discussion it is very clear, like 2 particle at least n are required, otherwise it will become 0, and determinant also shows that any 2 rows become equal, they are 0. So minimum n particles are required. So let us assume that for n particle problem, note that we are still talking of non-interacting problems where it is exact. For interacting, of course this will not be exact, because the theorem will no longer be true, the product. For only non-interacting case, the determinant is an exact, remember. So we are still discussing non-interacting, we will come to the interacting part in the next class, what happens for the interacting part, and that is where approximations will come. So let us now say you have n electron non-interacting, then I am still talking of an exact function now, and I require n spin orbitals, chi1, chi2, chi3, etc., which are generated from the eigenvalue equation of H. Remember, I have an eigenvalue equation for the one particle operator. If you note, I had written down H of 1, chi I of 1, epsilon I, chi I of 1. There are many eigenfunctions, okay? Like every one particle operator has many eigenfunctions, not one. One of them is ground state, then excited states, and so on, right? So I can generate n number of eigenfunctions, n number of spin orbitals, and then I can construct my wave function for a non-interacting n particle problem or n electron problem as an antisymmetric product. So let's say I take chi1 to chi n, then I can write down this determinant. Again, this is a normalization constant, you don't have to bother too much, but just like that, it is 1 by square root n factorial, and just like that, we can generalize it. The first row is chi1 everywhere, and the coordinates will keep changing till chi1 of n. Second row will be chi2, 1, chi2 of 2, so on till chi2 of n, and then like that you can go up to chi n of 1, chi n of n. I hope all of you can write this very easily now. So this has the hallmark that each row is characterized by one spin orbital, each column is characterized by coordinates. Note again, while I said this, you can trivially interchange the rows and the columns. So for example, you can say that one column will have chi1, one row will have one coordinate. It doesn't matter. Many textbooks may write it like that. It doesn't matter, you follow one particular convention. Okay. So we will follow this convention. So one of the row has one particular spin orbital, then automatically all products will come. How many products you have? Like for the two particle problem, we had only two terms, this minus this. For this determinant, how many product will have? How many set of n product will have? Like one of these chi1 1, chi2 2, etc. to chi n n. How many? N. That you have n factorial terms. In fact, that is the reason this 1 by square root n factorial comes, to normalize the whole thing. So every determinant, if I expand the determinant, I will have n factorial terms. Each of them will be a product of n functions. Okay. So first term will be a diagonal product, chi1 1, chi2 2, chi3, as if 1 is in chi1, 2 is in chi2, 3 is in chi3, and the rest of them will keep interchanging because electrons are indistinguishable. So that fact is recognized by the various other terms of the Slater determinant. Okay. So this becomes now exact solution for the non-interacting problem, however. But for the interacting problem, I can't still get an exact solution, but this will then become a basis for the interacting problem, to understand the interacting problem, and that is where we'll start in the next class.